This video will discuss the solution to question 22. If the oscillator in figure 2 somehow oscillates, the oscillation frequency in Hertz is, and then 8 possible answers are given for this oscillation frequency. To find the frequency of oscillation, we should first take a good look at the topology of this circuit, and we can recognize 3 subsections. The first subsection consists of these 3 identical RC sections, and we will refer to this as our frequency-dependent network, or beta. The second subsection consists of an operational amplifier of which the output is directly connected to its inverting input, causing it to be a unity gain buffer. Because the gain of this buffer is 1, it has no effect on the open loop gain. And the final subsection of the circuit consists of this inverting amplifier, which we will refer to as A. To be able to sustain oscillations at a certain frequency, the Barkhausen criterion should be satisfied. And that means that A times B times the effect of this unity gain buffer, which is 1, should be equal to 1. Since the gain of the inverting amplifier is always a real number, that implies that the value of our transfer of beta at our oscillation frequency should also be real. The transfer function of our frequency-dependent network will be given during the exam and is the following. As you can see, the denominator of this transfer contains some imaginary components, but we know that at the oscillation frequency, beta should not have an imaginary component. So we know that this term should cancel that term at the frequency of oscillation. And that will give us the following constraint. And if we solve this for omega, we will get that omega has to be the square root of 6 over RC. And since this is an angular frequency, so in radians per second, to get the frequency in hertz, we should just divide by 2 pi. So the final answer is square root of 6 over 2 pi RC.